next unit. The first thing we're going to talk about is the counting principle. Did you know that area codes were invented in the 1940s when the Bell Telephone Company realized they could not hire enough operators to handle all the long-distance calls that were being made? Bell researchers developed a system of 3-digit codes that would automatically route calls to long distance. We now call this the area code. Suppose in Texas we're going to add a new area code. The first digit must be a 6 or a 7, and the second digit must be a 0 or a 1, and the third digit can be a 3, 4, or 5. How many codes are possible? So we're going to show you in a tree diagram how we might think about this. So if the first digit has to be a 6 or a 7, that branches out to the second digit, which is a 0 or a 1, and then that branches to a third digit, which could be a 3, 4, or 5. So if you count in that third column, you'll see that there are 12 ways we could get an area code. So let's talk about lunch. Let's say you go to Sonic and you have these choices for entrees, 1, 2, 3, 4, 3 sides choices, 4 drink choices, and 4 dessert choices. So a tree diagram can help us start to think about this, but you can imagine this tree diagram might get pretty big if we drew it for all 4 of the entrees. So take a look. For just the hamburger alone, we have 3 ways to get our sides, 4 ways to get our drinks, 4 ways to get our desserts, and that would happen for every single one of the entrees. So each entree has 3 possible side choices. That makes 12. Each entree side has 4 possible drink choices. So now we're up to 48. And then each one has 4 dessert choices, which makes 192 total choices of ways we could arrange our meal at Sonic. The counting principle says if there are m ways of doing one thing and n ways to do another, there are m times n ways of doing both. So our Sonic example would have just been 4 times 3 times 4 times 4, which is 192. So in this next activity, let's say we have a murder mystery. We have suspects, rooms, and weapons, and we want to know how many possible combinations of these could happen. So we look in our suspects column, 1, 2, 3, 4, 5, 6. Rooms, 1, 2, 3, 4, 5, 6, 7, 8, 9 rooms. And then 6 weapons. So if I just do the counting principle, 6 times 9 times 6, I get 324 total outcomes. If I go to the jeans store, same rule applies. I have 1, 2, 3, 4, 5, 6, 7 times 4 times 3. I get 84 outcomes. And we can keep doing this with all of these different activities. The ice cream shop would be 3, 4, 5, 6, 7 times 3 times 3, which is 63 outcomes. And the same with Party City and the car dealership. And the movie theater. And the pizza parlor. Okay, so I think we got the hang of that. Oh, and Freebirds. There we go. There are 3 different types of probability we're going to talk about. The first one is, we're going to reminisce about middle school. If you draw 1 marble out of a jar containing 4 red, 2 blue, and 6 white, what's the probability that you draw a red marble? Well, there's 4 red and there's 12 total. So the definition of probability is the number of desired events over the total number of outcomes. I like to call this success over total. So success in this instance would be 4 red and the total would have been 12, and we reduce that to 1/3. So you have a 1 in 3 chance of grabbing a red marble. What percentage is that? So in your calculator, do 1 divided by 3 and you get 0.33333. And if you multiply by 100, you get 33%, 33.33%. All right, what if you have a die? That's singular for dice. What's the probability of rolling a number greater than 3? Well, that means you rolled a 4, a 5, or a 6. So this is the part where you would roll some dice and check in. You would roll maybe 10 rolls. You could do 20 if you wanted to. And you could use your data and compare it to your neighbor's data and see what's the probability you rolled a number greater than 3. And check with your neighbor and see if they're different. Why would they be different? Well, because this is an experiment. So you don't always get the same outcomes. So how can we determine the probability of rolling a number greater than a 3 without having to do the experiment? Remember, desired over total outcomes. Well, if I desire a number greater than 3, that's a 4, 5, or 6. So there are 3 numbers there. Total outcomes on my die, there are 6. So 3 out of 6 is 1/2. So what happened on your 10 rolls? Did you get half of them a 4, 5, or 6? What's the difference between theoretical and experimental? Theoretical is in a perfect world, what is supposed to happen. And experimental, of course, is us doing experiments, and it doesn't always happen perfectly. But the more experiments you do, the closer you get to that theoretical probability. So if we rolled the dice, say, 1,000 times, we would get closer and closer to the expected probability. All right, what's the probability I choose a king from a standard deck of playing cards? Well, a standard deck of playing cards has 52 cards. And if you didn't know, there are 4 kings. So 4 out of 52 reduces to 1/13. And that notation there, the capital P parentheses king, that's just the probability of picking a king. That's all that notation stands for. What's the probability of choosing a green marble from a jar containing 5 red, 6 green, and 4 blue? So green marbles, there are 6 of them, and my total is 15 marbles. So 6 out of 15 is 2/5. What's the probability of choosing a marble that is not blue in problem number 2? So we look at problem number 2 and we notice that 9 of them are not blue. So 9 out of 15. Or maybe I should count again and say 11 of them are not blue. So 11 out of 15. Sorry about that. What's the probability of getting an odd number if you roll a single 6-sided die? Well, 1, 3, 5. So I think that's 3 out of 6. 1/2 is your probability. Independent and conditional probability. Let's say you have 3 peppermints and 2 butterscotch candies in front of you. Doesn't matter if you like butterscotch, they're there. You close your eyes and you pick one. What's the probability you choose a peppermint? Well, there's 3 peppermints and there's 5 candies, so 3/5. You put it back. What's the probability you choose a butterscotch? Well, there's 2 butterscotch, 5 total, so 2/5. Why are these probabilities equal to each other? Because there's not the same amount in the pile there. What's the probability that you pick a butterscotch and then a peppermint? So you pick one, put it back, and then you pick another one. What's the probability you picked a butterscotch, put it back, then picked a peppermint? What do we do with the 3/5 and the 2/5? The and rule will tell us. The probability of A and B happening is the product of those probabilities. So in this case, we would multiply 3/5 times 2/5 and get 6/25. That's the probability I picked a butterscotch, put it back, and then a peppermint. What's the probability I pick a peppermint and another peppermint? Well, there are 3 peppermints. So I pick one, put it back, pick again. That's 9 out of 25. A jar contains 6 red balls, 3 green balls, 5 white balls, 7 yellow balls. 2 balls are chosen from a jar with replacement. That means I picked it, I looked at it, and I put it back. What is the probability that both are chosen are green? Well, there's 3 green, and there's 21 total. So 3 out of 21 times 3 out of 21 would give you 1 out of 49. Just use your calculator and let it reduce the fractions and do the calculations for you. You can do alpha y equals to get that fraction. 2 cards are chosen at random from a deck of 52 with replacement. What's the probability of choosing 2 kings? Remember we talked about getting a king was 1 out of 13. So 1 out of 13 times 1 out of 13 is 1 out of 169. Let's try this again. This time, you still got your 3 peppermint and 2 butterscotch candies. You close your eyes, you pick one, and you eat it. Or someone eats it. If you don't like butterscotch, give it to a friend. Then you do that again. What's the probability you chose a butterscotch both times? So let's think. Choosing a butterscotch, that was 2 out of 5. Well, I ate it, so it didn't go back. Now how many butterscotch and how many total? This is an and type of problem. If you eat one, how many are left for the second draw? How does that change? So I had 2/5 the first time, but the second time I only had one butterscotch and I only had 4 left. So that becomes 1 out of 10 because we reduced 2 out of 20. What's the probability you choose a butterscotch and then a peppermint? So butterscotch, remember, was 2/5. Peppermint, okay, there's still 3 peppermints, but there's only 4 candies left. So 2/5 times 3/4. And that gives you 3/10. Notice all the fractions are getting reduced, so let your calculator help with that if you want to. This is the same thing we just did, but with tree diagrams. Remember, 3/5 that I choose peppermint, 2/5 that I choose a butterscotch. And in the first scenario, I picked a peppermint, so this is what's left. So I have a half a chance of getting a peppermint, half a chance of getting a butterscotch. And down here, if I chose a butterscotch the first time, there's only 1 butterscotch left, and there's 3 peppermints left. And in the second one, I chose a peppermint. So now look at what's left. So there are my probabilities. 3/5 times 1/2, 3/5 times 1/2, 2/5 times 3/4, or 2/5 times 1/4. So we know we did it right because 10 out of 10 is all the total possibilities. All right, so here's a picture of some cards if you ever need to come back and look at these to refresh your memory on what kind of cards there are. A deck of cards is 4 suits. We have diamonds, clubs, hearts, and spades. We have 10 number cards. And then we have a jack, a queen, and a king. Those are called face cards. And then the ace, which counts as a 1. What's the probability I choose an 8 from this deck? Well, there's 52 cards. 4 of them are 8s. So I'd go with 4 out of 52, or 1/13. What's the probability I choose an 8 of clubs? That's this card right here. There's only 1 of those. So 1 out of 52. What's the probability I choose a face card? Now, all of these jack, queen, and king, those are all considered face cards. So if you look at that, you'd notice there are 12 of them. So 12 out of 52 reduces to 3/13. What's the probability I choose a jack or a queen? Well, there were 4 jacks and 4 queens. So this isn't an and type of problem, it's an or. The probability of A or B is the probability of A plus the probability of B. So I'm going to add up my 4 out of 52 for jacks, 4 out of 52 for queens, and get 8 out of 52. I think that reduces to 2/13. What's the probability of drawing a red or blue marker from a box that has 4 blue, 6 yellow, 2 black, and 8 red? So if you count those up, there are 20 total. And how many reds? There are 8 reds and 4 blues. So I'm going to add those together and get 12 out of 20, which is 3/5. What's the difference between an independent event and a dependent event? Independent is when the outcome of one event does not influence the outcome of the second one. Dependent is when the outcome of one event does affect the second one. What type did we experience when we chose one candy and ate it before the second draw? Okay, if I put the candy back, if I replaced it, that was independent because the second probability was identical to the first. If I eat the candy and I don't replace it, that's dependent because what I did the first time had a direct impact on what happened the second time. All right, conditional probability. The probability that event B will occur if event A has already happened. So there's my formula. The probability of B given that A happened equals the probability of A and B both occurring over the probability of A. So this time we're not choosing from our total, we're just choosing from what that given event, that conditional event that we know has already happened. At a middle school, 18% of all students play football and basketball, and 32% of all students play football. What's the probability that a student plays basketball given that the student plays football? So we've narrowed down our choices. We know that 32% play football. So that's going to go on my denominator because that happened first, given that the student plays football. So my numerator is the 18% that do both football and basketball. So 18 over 32, we're going to divide that in our calculators, 0.5625. And when you multiply that times 100, you get the percent, 56.25. So if I know they played football and I picked a person at random, there's a 56% chance that they played basketball too. 70% of your friends like chocolate. I'm assuming this is ice cream. And 35% like chocolate and strawberry. What is the percent of those who like chocolate also like strawberry? So what happened first? Chocolate. So that's my denominator, 70% like chocolate. My numerator is going to be the ones that like chocolate and strawberry. So 0.35 over 0.70. When you divide that in your calculator, you get 0.5, which is 50%. A jar contains black and white marbles. 2 marbles are chosen without replacement. The probability of selecting a black marble and then a white marble is 0.34. And the probability of selecting a black marble on the first draw is 0.47. What's the probability of selecting a white marble on the second draw, given that the first marble drawn was black? So there's your given that. The probability that we drew a black marble in the first draw is our denominator. The probability of black and white is our numerator. The black marble happened first, so it went on the bottom. So 0.34 over 0.47 is 0.7234, which is 72.34%. Remember, your probability always has to be less than 1, so your numerator is never bigger than your denominator. In the United States, 66% of all children get an allowance, and 31% of all children get an allowance and do household chores. What is the probability that a child does chores given that they get an allowance? Well, there's your given that. What happened first? The allowance. So 0.31 over 0.66 comes out to 0.4697, which means 46.97% of children do chores if they also get an allowance. Okay, so there's some more examples for you to try. So if you want to pause the video, take a look, and check to see if you got the right answer. Next one, again, pause the video, do your work, and then come back and check your answer. One more. Pause the video, check your work. Remember the given that goes on the denominator. There you go. And that brings us to the end of today's lesson.